Thanks for sticking around. It's nice to see some familiar faces and some unfamiliar ones. For those of you that don't know me and you're wondering about my accent, maybe. So I'm Dutch, okay? I spent some time in the United States, but I'm Dutch. I grew up in Voorburg, here in Zuid-Holland. Maybe some of you recognize Den Haag, right? The Hague, the seat of our government here in the Netherlands. So this is close to the sea. I could ride my bike to the beach. It was great. England sort of somewhere over here, drifting away, right, from mainland sort of Europe slowly. I grew up in Overbergkade, 53. Not super interesting necessarily, but it was very close to this place here, Hofwijk, which is right where the train station is nowadays. It used to be a big garden here. There's another interesting story about Roman settlements here that I don't have time to go into. You can ask me later if you're interested in Romans, maybe, for a different time. And Hofwijk is the summer home of the Huygens family. So this is a close-up. It was built in the 17th century by Constantijn Huygens, who was he was lots of things. He was a poet, politician, diplomat. He spent some time in England also. He was even knighted. I just found out reading his Wikipedia page by King James I. He was a secretary to the stadtholder in the Netherlands. And to get away from, so he worked in Den Haag, right, where all the politicians were, and to get away from the hustle and the bustle there, he built this summer retreat in Voorburg. At the time, it was sort of none of this stuff was there, right? So there was no train track and no major highway coming through. He had 5 children, 4 sons and a daughter, and one of them was Christiaan Huygens, famous Dutch polymath and scientist. Those of you that took my first year Intro to Astro course, you've forgotten everything, I know, because your exam was in January. But Huygens worked on the nature of light, for example, right? He worked on collisions, conservation of momentum. He discovered Titan. He realized first that Saturn's rings are actually rings, right? Galileo, with his inferior telescope, it was, by the way, invented by another Dutchman, right? He thought they were ears connected to the planet, but no, they are in fact rings. And Christiaan would spend a lot of time living in this house. His contributions to science were well recognized at the time already, right? Here he is at the foundation of the French Academy of Sciences, Louis XIV, in 1666, right? Sorry, year of I guess the Great Fire, is that right? So the French were having a better time. There's a lot going on in this picture. Interesting symbols, right? The Sun King in the center, and then all these people studying planets and comets orbiting this sort of I don't know. Again, for a different time. Later in his life, Huygens published his maybe more controversial book, the Cosmotheoros, in which he sets out sort of his vision for life amongst the stars, for life in the universe. And he says, I'm paraphrasing because he wrote it in Latin originally, but he says basically 3 things. Exoplanets should be common, right? The stars, this is from the English translation, stars have planets about them just like our sun. These planets are like the Earth, right? So many suns, so many Earths, they have seas and mountains and all of that. And therefore, they are also stocked with many herbs, trees, and animals. So they have life, right? So there's planets everywhere, they look like the Earth, and therefore they have life. That's what he said. And even though this was published in 1698, a few years after his death, if you were paying attention to the dates on the previous slide. So even though Huygens was living in the liberal sort of Netherlands, right, he was slightly embarrassed maybe by some of these points, and he decided to push off, to hold off with publishing it. It was published by his brother after he died. Because remember, right, in 1600, not that long ago, Giordano Bruno was burned at the stake in some piazza in Rome for voicing, well, pretty similar opinions or ideas. So we can now, we've come a long way since 1698, so we can see whether his predictions rank true or not. That's sort of my story here, or my frame. Going back to Simon's talk. So the first one, we know it's true, right? There's exoplanets everywhere. 5,000 or so have been discovered since 1995. Many of them are very big, not necessarily because all the exoplanets are big, but because these are easier to spot, right? They affect they induce this wobble in their host star, or they have deep transit signatures, so lots of gas giants. Some of these intermediate planets, super Earths, these are interesting. because they're very common, and we don't have an analog for one of those in the solar system, which is why we don't have a good name, right? It's sort of Earth, but super. It's just bigger. Not necessarily better. And then 4% of these 5,000 or so are small, rocky, terrestrial planets. Small fraction of that 4% fraction, maybe a dozen or so, orbit in what we sometimes call the habitable zone, right? So they have orbits that are not too close to their star, where it's very hot, and also not too far from the star, where it's too cold. They sit sort of in this nice Goldilocks zone. I have, at great risk of sort of a personal harm, I have investigated these limits by spending 3 years at the University of Chicago, where during the winter time it's incredibly cold, and 2 years at the University of Arizona, where during the summer it's pretty hot. So if you're ever looking for, I don't know, well-defined limits to the habitable zone, I can tell you that, yeah, summers in Arizona, winters in Illinois is basically where at least this organism stops functioning very, very efficiently. We know, even though we've only found a couple of these planets, we know how many we've missed. We know our detection bias really well. And so we can estimate this number that scientists call eta Earth, usually. It's the frequency of Earth-like planets around Sun-like stars in the habitable zones. This is the same number that Rafi had up earlier. I wrote it in a different notation. So this is just saying, if I translate it, and I picked different papers, so it's slightly different, between 2% and 88% or so of stars have an Earth-like planet in their habitable zone. Yeah, similar conclusion to what Rafi had earlier. That number is huge, right? It means, even though it's a bit uncertain, if you go out at night, you pick 5 stars at random, one of them will have a planet, on average, about the size of the Earth, in this sort of temperate region here. But there's a problem. We really don't know anything about these planets. We know their size, roughly, right? It's between 1 and 2 Earth radii, or a bit smaller, or something like that. We know their orbit, kind of, but other than that, we don't know anything. So the question is, are these Earth-sized planets now? Are these Earth-like? A little bit, maybe. And what does being Earth-like mean? So this touches on some of the themes that Dr. Haywood spoke about earlier. She showed an Apollo 11 image. I show an Apollo 8 image. We didn't coordinate this. I like to pick Apollo 8 because it was the first time that humans really left the Earth's gravity, right? They were no longer in orbit around the Earth. So it's looking back from the moon on Christmas Eve. You see the Earth. What makes the Earth Earth-like is an interesting question. You can think about it for a long time. You can approach it from many different angles. Answers that often come up when I give talks like this in outreach settings is like liquid water on the surface, right? It's very obvious when you look at this image. It's water all over. There's an atmosphere. You see clouds, you see winds, etc., oxygen. Maybe the moon that's lurking here in the foreground, maybe that's important. It's an interesting discussion what the moon did for maybe origin of life, or also just sort of to spark the scientific revolution. The moon had a very interesting sort of double role. We can talk about it later if you want. Plate tectonics came up. Is life what makes Earth Earth-like, right? In this idea with Gaia and life influencing the evolution of Earth and climate. Or is it intelligent life and culture? I don't know, maybe. So all interesting questions. We don't know the answers to these for exoplanets. And in fact, for Earth, one thing I like to stress, this water always comes up, but the Earth is extremely dry, okay? If you compare it to, for example, the sun, or other bodies in the solar system, or materials in the interstellar medium. If you take all the water on the surface of the Earth and in the mantle, you can fit it into this tiny sphere here, and you will find that it makes up less than a fraction of a percent of the total mass of the Earth. This is very, very, very dry, okay? You can compare it to other bodies, as I mentioned, especially moons in the outer solar system. So again, Titan, discovered by Huygens. Pluto, no longer a planet. Sorry, also interesting, right? It used to be the only planet discovered by Americans. And then we voted in Prague, in Europe, to demote it, right? Just to sort of, so this is not anymore. But look at that. All these have huge water contents, right? Huge water reservoirs. Earth is very, very, very dry. And yet, if you look at the surface, you see water everywhere, right? This is a picture of my 4-year-old looking for fossils on the Jurassic coast. We see water here in the oceans, in the sea. We see oxygen, basically just water in the atmosphere. And then we have carbon-based, intelligent, maybe, life forms, right, scurrying around on the surface. The Earth is also very much depleted in carbon and nitrogen, by the way. So nitrogen that dominates the atmosphere, the oxygen in the water, and the carbon in these critters are all very underabundant on the surface of the Earth, and yet they're very important for life, right? Clearly, and not just for life today. This is not that long ago, but we know there's been life on Earth for hundreds of millions of years, right? Billions of years. On the Jurassic coast, you can pick up ammonites. This one's in mudstone. Tobias was very proud for finding this one. So you know that life has been around for a long time, and you know that the conditions for life, so relatively, reasonable temperatures, things like that, have been around for a while. And again, in those feedback cycles that make that possible, oxygen and carbon play a big role. So, for example, in the carbon silicate cycle, right? Let's say for some reason the Earth gets a little bit warmer, you'll evaporate more water, more clouds, leads to more rainfall, more erosion, more weathering of the surface. That leads to carbon being sequestered, drawn from the atmosphere, being sequestered in the mantle. That reduces the amount of greenhouse effect and lowers the temperature again. So it's like a thermostat that acts on very long time scales. So carbon, oxygen, important for life and for sort of climate, but underabundant. What about these alien worlds then, right? What about these planets? I don't know, every 5th star has a small exoplanet. Do those have similar cycles? Do those have carbon, oxygen? Right? We don't know. You could ask. Actually, Marco asked, right? Why, when we look for aliens or life in the universe, why do we focus on sort of life as we know it? It's a good question. So I'll point you to these papers. You could look at sort of astrobiology roadmaps. It's not, Rafi gave a good answer. We have to start looking somewhere. But also carbon and oxygen, they are just marvelously good elements for life, and they are very abundant in the universe. So Carl Sagan, do watch his sort of original Cosmos show from the 80s. He phrased it this way. He said, "I am reluctantly a self-confessed carbon and water chauvinist," right? These are just wonderful elements to build life from, and you can find them everywhere in the universe. But also, much like Marco, Carl wondered, could my fondness for these materials have something to do that I make chiefly of them? Probably, but still, right? We need a place to start. So how do we characterize the inventories of these elements on exoplanets? Well, Rafi showed one idea. You could do sort of spectroscopy. You could look for signatures of gases made up of these elements in the atmosphere when you see them from really far away. You saw the spectrum of the Earth. We're not at a point where we can do that for exoplanets that are many, many light years away. Maybe in the next. Well, it will be possible probably in our lifetimes. I want to present an alternative idea. Alternative idea is to look and try and understand the formation of planets, and then say something about what that means for their composition. So we know. Big picture we know pretty well, and we've known since the 70s, is that planet formation is a byproduct of star formation, basically. You start with a molecular cloud in some spiral arm of some galaxy. That becomes unstable, collapses, forms a disk, right? Conservation of angular momentum, yada, yada, yada. You form a star in the center, and ultimately this disk, originally composed of gas and small microscopic dust particles, it dissipates. Small dust particles combine, grow, stick together, and form a planetary system. And the properties of the planetary system at the end, both the architecture of the orbits and the masses and the sizes of the planets, but also the compositions of the planets, reflects this sort of long star-planet formation journey. So we can try to piece things together. For example, right, we're all familiar with the solar system, 4 small planets, 4 big ones. Just to remind you, these were discovered only quite recently, and again, no Pluto. Just the fact that all the planets lie more or less in the same plane, go around in the same direction, that immediately tells you they formed from this flat, rotating protoplanetary disk. The idea is then small ones formed in the inner regions where it was hot, there was no water ice, yeah, so they're rocky, they don't have lots of water. And then further out, you had water ice freezing out because these disks have lots of water. The ice helps to grow big planets and you form giant planets. That was sort of the story. It's also very interesting to look at regions where planet formation failed, right? Where planets did not grow. So we have the asteroid belt and the Kuiper belt, named after another Dutch guy. Sorry, I keep it's by accident. I can't help it. And these regions are great because we can see sort of intermediate stages of this planet formation process. And in particular, you can launch rockets, right, and missions to Mars and asteroids and whatever. It's very expensive, and you need to, yeah, it just sounds like a lot of work. You can also just wait on the Earth, wait for two asteroids to collide, produce lots of fragments. Every now and then, one falls for free, right, in your backyard. So this is anyone know where this is? Meteor crater in Arizona. This was created by some 50,000 years ago, I think, somewhere in the Pleistocene, by a 50-meter sized iron meteorite that impacted at something like 20 kilometers a second. At the time, by the way, climate here was different, so this was all sort of a forest and woodlands. Left a big crater. In case you're interested in seeing what an iron meteorite looks like, I brought a prop. So I have here University of Exeter's Astro Department, I don't know, mascot, iron meteorite. This is not from this one. This is part of a larger 4-meter-sized body that fell in Argentina 5,000 years ago. There's an interesting story in terms of how we know that it's that old. It's very heavy. It's made of iron. You're welcome to come have a look at it, pick it up. It survived falling to Earth, right? So it'll survive a couple of space enthusiasts handling it. That's an iron meteorite. Those formed from asteroids that differentiated, melted, right? So all the iron went to the center, end up in the fragment. But if sometimes you can find very primitive meteorites that did not melt, they did not heat up. And then if you cut them open and you investigate them sort of up close, you'll find that they contain minerals and materials, I don't want to go into the details here, that have very different thermal histories. So this is a scale of a millimeter, right? This is tiny. You have chondrules, CAIs, calcium, aluminum-rich inclusions. These are formed at either very high temperatures, have never seen high temperatures, something in between. We can estimate the cooling rates. They all come together and they're sort of close together and intermixed at these very small, very fine scales, right? So this immediately tells you that planet formation is a very messy process with lots of transport, material flying through the protoplanetary disk, coming into the inner disk from the outer regions and vice versa. So it's a messy process. That's the solar system. I could talk for a long time about the solar system. Some of you probably know. I can ask me later. But I want to talk about exoplanets, right? So how do we study planet formation around exoplanets? Well, we can use interferometers. Thank you, Ollie, for explaining what an interferometer is. I can sort of fast forward. One we use a lot for studies like this is the ALMA, Atacama Large Millimeter Submillimeter Array in Chile. This is actually a movie, so there's a car for scale. Right, so Space Exe has one small radio telescope, and ESO, the European Southern Observatory, has 144 or so of them, and bigger ones. These, the radio signals they detect are combined, and effectively they operate as a very big telescope. Right, yeah, exactly, baselines of up to 16 kilometers, very high up, somewhere on the mountain top in Chile. When you combine all that data, you can get very good angular resolution observations. So here's an example. This is a baby protoplanetary disk. Scale here is about 100 astronomical units, observed by the ALMA observatory. This image was, the data was reduced and sort of and put together and presented by a PhD student working with me, Adrian, who's now he's a PhD student here, but spending some time in exactly. I shared it with him already. He's spending some time at ESO in Munich. And this is him, I think, in Sweden. I'm not exactly sure. So what you're seeing here is the thermal emission of small millimeter-sized dust grains that are on the way to forming a planetary system. Yeah, it's roughly the same, the right size already, about 100 AU. So this is the orbit of, I don't know, Pluto, something like that. But the bodies are still small. And we can do this for many different disks. This is from the D-Sharp survey led by Sean Andrews at the CFA, Harvard in the United States. All of these are baby planetary systems. Again, you're seeing the emission from the small dust grains. And what you see is that there's very rich variety, but also that there's all this structure, right? Some are small and smooth, some are bigger, and they have all these rings and gaps. That was very unexpected. People had, well, I had expected, this is very recent, I expected them to be very smooth. But they have all these rings. And nowadays we think that these rings are actually being carved out by forming giant planets that are then gravitationally perturbing and accreting material in these disks. Yeah, right. But however, the problem here is we cannot see the inner. That's okay. We cannot see the inner 1 or 2 astronomical units. So the regions where these planets are forming that will end up in the habitable zone, the planets that we think maybe yes, no are Earth-like, those are forming here very close to the central star, and we don't quite yet have the angular resolution to see those. And also, this thermal emission from the dust grains doesn't really tell us anything about the composition of the grains all that easily. You can kind of do it, but it's very complicated. So what we do instead is we turn to a different wavelength. We turn to the infrared, right? Wavelengths in micrometers now. It's a complicated plot. I'll walk you through it. We don't use ALMA, but we use the Spitzer Space Telescope because the Earth's atmosphere, as you know, is sort of opaque to infrared radiation. So we have to go to space. We launched a space telescope in 2003, for example. And then without resolving spatially these disks, you can observe, you can take a spectrum, and this contains like a fingerprint of all the different molecules that are present in these protoplanetary disks. So, for example, you see hydrogen cyanide, HCN, right, toxic, I guess, to humans, carbon dioxide, CO2, acetylene, C2H2, and all these other lines, it's not noise, all these other lines are water. So the gas in these protoplanetary disks is very rich in water. Top half is an actual observation of AA Tauri in this case, in Taurus, and then the bottom half is a model. This is from 2008. And now this is where it gets kind of interesting. This is emission from molecules coming from the inner few AU. So this is really almost the regions where the terrestrial planets may or may not be forming. You can compare the sizes of these peaks and get sort of ratios between the line flux ratios or almost sort of abundance ratios maybe of different molecules, which is what we did here in 2020 by a paper led by Andrea Banzatti at the University of Texas. I was part of this study, it was very exciting. So what he did, he mapped for I don't know, 24 disks. Each point here is a disk, a protoplanetary disk. For each of them, he found the ratio of water to hydrogen cyanide. And then he plotted that against the size of the disk as measured by this ALMA interferometer. And he's very brave because he drew a straight dashed line as sort of in true astronomer fashion. But it is a statistically significant result. Okay, also. So what we tend to see is that disks that are small, so on the left of this plot, have a higher H2O to HCN ratio. It still sounds confusing. But really what we're seeing is that small disks have more water in their inner regions. And this was a very unexpected result because this chemistry that you're sort of probing or tracing is really coming from close to the star, while this is coming from hundreds of AU. So we were not expecting this correlation necessarily, although we were building on the earlier work that found something similar by Joe Najita at the University of Arizona. So it's very, very exciting. Here's the story that we came up with. We think that if you imagine a protoplanetary disk, sort of in purple here, with a forming Earth-like planet inside the water snow line, so in this blue oval shape, temperatures are so high because you're close to the star that water is present in the vapor phase, in the gas, so it's blue. And out here, all the ice, all the water is frozen out on dust grains and other particles. So you have water vapor inside, water ice further out. We think that for these small disks, the ones that are smooth, that there's been a period of intense inward migration of materials, of ice-rich materials, and that has elevated the water content in the gas in the inner disk. That's our story. Alternatively, and it has shrunk this disk, right? So that sort of matches that story. And then alternatively, if you have a big giant planet like Jupiter sitting out here, this can block the influx of these small icy solids, and it keeps the inner regions more sort of nice and dry. That explains these observations. And we're now revisiting this by getting better data, not with Spitzer, but with James Webb. I tried to draw them to scale. So Spitzer has a or like 85 centimeter mirror, and is sensitive to the infrared. It stopped operating in 2020, but now we have the James Webb Space Telescope, right? Mirror diameter 6.5 meters in L2. It launched around in December. I watched it with my kid. It was fun because he was about the same age when JWST was launched. He was 4, and I was 4 when the Hubble Space Telescope was launched. So it's truly a next generational sort of instrument. I'll touch on the cost later. With JWST, you can get much more accurate spectra, both because of the increased size of the mirror, but also it just has better instruments. We're we're a few decades further. So we'll revisit this. As we speak, JWST is observing about 24 disks as part of Cycle 1 programs that I'm involved in. We have something like 60 hours on this awesome machine to look for water and other small organics around in protoplanetary disks, basically. I have a couple spectra. I don't think I'm allowed really to show them. And we're still working on the reduction. So you have to come back to this conference again next year, and I can show you sort of preliminary results. Last thing, because I think I'm sort of out of time. That's the disks, right? So I tried to convince you that there's a huge variation in the water content of the inner regions of the protoplanetary disks. Does that somehow change the properties of the planets that we find? Well, maybe, right? This is a plot from a recent paper that was published in Science. All the points here are actual, known, measured exoplanets. This is a small sample of the best studied, best characterized exoplanets. You get an accurate measure for the radius from a transit technique for those of you those of you interested in exoplanet detection. You get the mass from radial velocity, and then you plot both of them on the same plot, and that gives you an idea of the density of the planet. Right? All the points on this green line have a density that is similar to that of Earth, which is this green circle, and all the points on the blue line have a density that's comparable to having 50% water and 50% Earth-like composition. And what you see is that most of the planets actually fall on either one of those curves. And this subset of planets, these are only planets that are found close to the star. So they should all be dry, and yet some of them have what looks like 50% water. It's a huge reservoir. I'll talk about it later. This plot here is the same sort of figure, but these are planets that have been made in a computer by 4 very talented undergraduate students, Daisy, Tom, Tylo, and Ben Derriar, who are working on their MPhIS project with me. They're now in their 4th year. They started working on this last year. They have simulated numerically this process of planet formation, including this inward migration of pebbles and solids, and followed where the water is. And they can kind of, in some cases, they can form both of these classes of planets, right? These would be the water-rich ones. These would be the dry ones. They have some in between that may be here. So they're sort of trying to compare this, and we're thinking about how to wrap that project up. So it's very exciting, I would say. And just to end, I just want to say that 50% water is really crazy, right? I told you at the beginning that the Earth has a fraction of 1/10% water. So we have exposed sort of land, and then you can discuss sort of how all these elements that are so essential for life, how they are cycled between the mantle and the atmosphere and the oceans and et cetera, et cetera. If you have a water world, Simon touched on, all the way at the end, he asked for more water or ocean planets, right? So here they are. If you have a very deep ocean, this doesn't work, right? There's no more direct interface between the land and the atmosphere. So this carbon silicate weathering cycle, for example, that I showed, that breaks down. So there's no more stabilizing feedback. If the ocean gets really thick, you'll develop a layer of high pressure ice at the bottom. So then you don't even have a connection between the water and the rock anymore. It's very different worlds. And in fact, this is also problematic for looking for biosignatures, because just to come back to what Rafi said, oxygen is usually seen as sort of in combination with other molecules as a biosignature. But on water worlds, you can actually get abiotic oxygen in the atmosphere just by efficient sort of photolysis of the water in the ocean. So potentially it can complicate the way in which we interpret these biosignatures. This is from a review paper I'm working on, but you don't have to take my word for it. You can ask Kevin Costner in 1995 classic Waterworld. I have a point here to make, just sort of to end. So in 1995, which was the year the first exoplanet was discovered, Kevin Costner came up with Waterworld, which was, I think it's considered a flop, but I think it's a very enjoyable movie. At the time, it was the most expensive movie ever made. And it cost $175 million to make, which, adjusted for inflation, is something like $330 million today, which is only about 1/30 of the cost of the James Webb Space Telescope. So if you think James Webb Space Telescope is expensive, Waterworld is 1/30 of the price. Okay, so it's either 30 Kevin Costner movies that were not very well received, or a space telescope. I don't know the answer. It's a tricky one. I really like Kevin Costner's work. So just to wrap up, I come back to Christian Huygens. I forgot to mention his hairstyle, which I'm trying to slowly sort of emulate. Exoplanets should be common, yes, right? It's true. These planets are like Earth, well, yes, but not all of them, right? We found all these weird hot Jupiter ones and very exotic planets. But yes, lots of them are also like Earth. These planets host life. Well, we don't know. We don't know. We'll find out maybe in our sort of in the, I don't know, next 10, 20, 30, 40 years. One interesting question that I sort of touched on is that we may need to think about what it means for habitability not to have too little water, but to have too much of it. That's my story there, and I'm happy to take any questions. And yeah, come up and check out the meteorite if you want to stay around. Thanks.